Hey there, and welcome. Today, we're diving into a bit of a geometric detective story. We're going to explore two of the most fascinating triangles you'll ever meet. Now, they might look pretty simple, but trust me, they're hiding some seriously elegant mathematical secrets. So, let's get started.
We all learn that triangles are these fundamental building blocks for everything, right? From bridges to computer graphics. But today, we're not talking about just any triangles. We're zooming in on two special cases, ones with these perfectly predictable, almost magical properties built right into their DNA. So here's our mission. We're going to prove these properties. We're not just going to state them as facts and call it a day. Nope. We're going to use pure logic to uncover why they're true. Think of it like we're cracking a code that's been hiding in plain sight this whole time.
First up, we've got a real classic, the 30-60-90 right triangle. This one is a favorite for architects and engineers, and for a very good reason. There's this very specific claim about how its sides relate to each other. And you know what? We're going to put it to the test.
Okay, here's the case file. The claim is really simple. The side opposite the 30-degree angle, that's the short leg, BC, is precisely half the length of the longest side, the hypotenuse, AB. I mean, that seems a little too neat to be true, doesn't it? Let's see if we can prove it step by step. All right, so our first move, and this is the crucial one, is a clever little construction. We're going to pick a point, let's call it D, on the hypotenuse AB. And we're going to place it with one very specific condition. The new line we draw, CD, has to be the exact same length as the short leg, CB. This single step is what's going to unlock the whole puzzle.
And right away, this move has a really cool consequence. Because we force CD to be equal to CB, the new triangle we just made, CBD, is by definition an isosceles triangle. And what do we know about isosceles triangles? The angles opposite the equal sides are also equal. Since we already know angle B is 60 degrees, that means angle CDB must also be 60 degrees.
Now hang on a second. If two angles in a triangle are 60 degrees, what does the third angle have to be? Well, 180 minus 120 is 60 degrees. So this triangle isn't just isosceles, it's actually equilateral. All its angles are equal, which means all of its sides have to be equal too. So now we know for sure, the side BD is the same length as BC. So our little construction split the big triangle into two smaller ones. We've just cracked the code on triangle CBD, so let's turn our attention to the other one, triangle ACD. We know from the very beginning that angle A is 30 degrees, but we can also figure out angle DCA pretty easily. The whole angle at C was 90 degrees, right? And we just found that the angle BCD is 60. So 90 minus 60, that leaves us with 30 degrees. And look at that, we found another isosceles triangle. Since two of its angles are the same, they're both 30 degrees, that means the sides opposite them have to be equal. So side AD must be equal to side CD. This is the final piece of evidence we need. Okay, let's put all the clues together. From that second isosceles triangle, we proved that AD equals CD. And from our equilateral triangle, we proved that CD equals BD, which also equals BC. It's like a chain reaction. We've just shown that four different line segments, AD, CD, BD, and our original short leg BC, are all the exact same length. So here's the final step. The entire hypotenuse, AB, is just its two parts added together, right? AD plus DB. But wait a minute, we just proved that AD is equal to BC, and we also proved that DB is equal to BC. So we can just substitute them in. The hypotenuse AB equals BC plus another BC. In other words, it's 2 times BC. The short leg is exactly half the hypotenuse. Case solved.
Awesome. Now, let's move on to our next mystery. And this one is a little more exotic. It's an isosceles triangle with a very particular set of angles, 36, 72, and 72 degrees. It's known as the Golden Triangle, and believe me, it has earned that name. So here it is, and the big claim is this. If you take the length of one of the long sides, say AB, and divide it by the length of the short side, BC, you get a very, very famous irrational number, the golden ratio, phi. This is the number that seems to pop up everywhere, from seashells and flowers to classic art, and even the geometry of a pentagram. Let's see if we can find it hiding inside this triangle.
All right, now this proof is a little different. It's going to start with a clever geometric construction, just like the last one, but it's going to lead us right into the world of algebra to find the answer. So let's get into it.
So once again, our first move is a smart construction. We're going to draw a line from corner B over to a point D on the opposite side, AC. And we're going to draw it so that its length, BD, is exactly equal to the short side of our original triangle, BC. Okay, let's take a look at the angles in this new little triangle we just made, BCD. Since it's isosceles, we know that angle BDC has to equal angle C, which is 72 degrees. So that means the last angle, CBD, has to be 36 degrees to make it all add up to 180. But wait a minute, 36, 72, 72? Those are the exact same angles as the big triangle we started with.
And that, right there, is the key to this whole thing. When two triangles have the exact same angles, we say that they're similar. It just means one is a perfectly scaled down version of the other. And the most important thing about similar triangles is that the ratios of their corresponding sides are equal. This is the bridge that's going to get us from geometry to our final answer.
So that similarity lets us set up this incredibly powerful proportion. The ratio of the long side to the short side in the big triangle, that's AB over BC, has to be equal to the very same ratio in our new smaller triangle, which is BC over CD. Okay, time to switch gears to a little bit of algebra. Let's call the long side x and the short side y. Our proportion now becomes x over y equals y over, what's CD? Well, the whole side AC is the same as AB, so it's x. And if you look closely at that third triangle we made, ABD, you'll find it's also isosceles, which means AD is equal to BD, which we know is y. So the length of CD is just the whole thing, x, minus that little piece, y. And this is where the real magic happens. The ratio we're trying to find, x divided by y, that's phi. So if we substitute phi into that equation and do a little rearranging, we get this beautiful, simple quadratic equation, phi squared minus phi minus 1 equals 0. And when you solve that equation for its positive solution, what do you get? You get 1 plus the square root of 5, all divided by 2. That is the precise mathematical definition of the golden ratio, phi. The claim is proven. That incredible number is literally baked into the very structure of this triangle.
So, let's just take a step back. What did we just see here? We've walked through two completely logical step-by-step proofs. We didn't need a ruler, we didn't need to measure a thing. We just used pure reason to uncover these undeniable properties hidden inside these simple shapes.
On the one hand, we had a proof that used a clever construction to reveal hidden equilateral and isosceles triangles. On the other, we used the concept of similarity to build a bridge into algebra. Both of them started with a simple shape and ended with a perfect, unchangeable mathematical truth.
It really makes you wonder, doesn't it? Geometry is just full of these hidden rules, in shapes like the 45-45-90 or the equilateral triangle. What other elegant truths are just sitting there waiting to be found, not just in a textbook, but in the patterns of the world all around us? Thanks for coming along for the investigation.